Okay, good morning, everybody. So what I'd like to do today is finish up our chapter on earthquakes. Just have a little bit more left to go through. And then we're going to start a new chapter on geology and your health, which might not sound all that hazardous, but I think after I cover a few of the topics, you'll see that it's probably the hazard that's affecting you the most right now. You guys, just by breathing in here, are actually in somewhat of a hazardous environment. And it's not because of COVID. I mean, that actually makes it worse. But there are things in our atmosphere and things around us that can greatly affect our health, and it's kind of invisible to us. But we'll get to that in a minute or so. So, at the end of last class, we had switched from talking about tsunamis, which are one of the sort of side effects of earthquakes that can be hazardous, and started talking about what can we do about these hazardous earth processes, earthquakes. Can we predict these things? And I showed a little video at the end of last class that kind of went through and discussed all the difficulties that we have when it comes to trying to predict earthquakes. We're terrible at it. We suck at it. And I don't know if we're going to get much better at this, at least during my lifetime, unless there's some new invention of some new technology that allows us to see things we haven't been able to see before. Because remember, this is all taking place inside the earth, well beneath the earth's surface, and we just can't see down there. We can't really gather the information that we need from deep in the earth that helps us to predict these hazardous earth happenings. So that's not stopping us from trying, though, and what I want to finish class with today is just looking at some avenues that scientists are currently using to try to come up with better ways of predicting earthquakes and then warning the general public. The first one I have here is something called a seismic gap. Okay, a seismic gap is an area or a stretch of a fault line that hasn't experienced an earthquake in some time. And probably the best example of this is the San Andreas Fault in Southern California. So we know that there are sections of the San Andreas Fault that have had lots of earthquakes. If you look at the southern part of the San Andreas Fault, just outside of San Diego, up to LA, lots of earthquakes in the last 100 years. And then there's a stretch of 100 to 200 miles where there haven't been any earthquakes, a little farther north of that. And then another stretch even farther north that have lots of earthquakes. So you have lots of earthquakes in the southern part, lots of earthquakes in the northern part, and no earthquakes in the middle. And what we think that represents is a locked section of the fault that isn't moving. It's clearly moving to the south. It's clearly moving to the north. It should be moving in the middle, but it's not. So it seems that something has locked that fault in place. Stress is continuing to build up clearly because the southern part of the fault is moving. The northern part of the fault is moving. But this lock section between LA and San Francisco, there's a little town out there called Palmdale that gets a lot of attention because it seems to sit sort of right in the middle of this seismic gap. This area hasn't had a big earthquake in well over 100 years, and it should have. So this doesn't tell us that an earthquake is going to happen there. Eventually an earthquake is going to happen there. We just know that this is an area of interest that should experience a large earthquake pretty soon. So it sort of helps us narrow in on areas that might be a danger in the near future. And because the southern part of this fault is moving and the northern part of this fault is moving, but this middle part is not moving, it suggests that it's had a century or so to build up an awful lot of stress. And the fear is that when it does have an earthquake, it's going to be really big. So what seismic gaps allow us to do is focus in on areas that we think are especially hazardous. We can say, this area is overdue for an earthquake. But it doesn't tell us when it's going to happen. It doesn't tell us it's going to be next year, 5 years from now, 10 years from now. We just know that over time, it's probably going to be more and more hazardous as more and more stress builds up and is not released through additional earthquakes. So again, it does not enable us to pinpoint the time of the next earthquake. It just gives us an area to be concerned about. And that's not terribly useful for us. But it does give us areas that we can concentrate our geologic studies on, because we know one's going to happen there eventually. So we can study these areas, look for things that are happening, and maybe we'll notice something prior to the next big earthquake that we can use as a tip-off for earthquakes there in the future and earthquakes in other regions as well. What we really need is something that gives us an alert, that warns us that earthquake's going to happen, and it's going to happen soon. That's what we really want. We want to be able to narrow the time that we think the earthquake is going to occur over so that we can warn people. So they're not in tall, unstable buildings, and they're not driving under double-decker freeways that can collapse. We want to give people warnings so that they can prepare properly. So what we need is some sort of tip-off from the earth that says, hey, I got something I'm sending your way here pretty soon, and it's not going to be pleasant. So we've been looking as scientists for telltale signs of earthquakes for a long time. And there are some. And what I'll do here is sort of go through the things that we've noticed that happened before an earthquake, talk about their potential as a tip-off for impending earthquakes, and some of the problems associated with using these observations as a prediction tool. So this first one I have here is something called a microseism. Micro meaning small, seism meaning quake or earthquake. So these are tiny earthquakes that happen before a big earthquake. Okay, I have this pen, but pretend it's a pencil, because pencils break nicely. So if I start flexing this pencil, right? If I keep flexing it, what's eventually going to happen? It's going to snap, right? Well, when I was in grade school, remember, you always had to buy those number 2 pencils, always on the list of stuff before school started. And whenever I'd be bored in school, I'd sit there and flex my pencil. And I could tell when it was about to break. I could always tell because I could hear it start to crack. And that's exactly what's happening here, is that you're building up stress in the earth, and right before it's ready to snap, you start to hear the weak spots breaking. Just like in the pencil, you start hearing the weak spots in the wood start to give way. So it's not unusual for right before a big earthquake that we get lots of small earthquakes. The problem with this is that sometimes these small microseisms happen only seconds before the big earthquake comes in. And that's not enough time to warn anybody in any substantial way that can help them. And maybe even worse for scientists is that sometimes we get microseisms and then nothing. An area starts to crack, and then it just stops for a while. And as a scientist, what's really important, especially if you're working with the public, is to have credibility. I mean, if you look at the political landscape today, that's one of the big problems out there, is that everybody's trying to cut into everybody else's credibility, and scientists' credibility is getting questioned all the time. And when people don't trust scientists, then people don't listen. So what we don't want to do is have a bunch of microseisms, put out a big earthquake warning, and then have nothing happen. Because what's going to happen next time we try to help the public by predicting an earthquake? They're going to say, "These morons got it wrong last time. I'm not going to listen to them." So we want a warning system that's going to work. We don't want to put out false warnings because it just makes things worse down the road. And with microseisms, sometimes they tip off an earthquake and sometimes they don't. So that's one of the reasons why we don't use it as a warning system today. This next one I have listed here, the rise of water levels in wells, is actually related to the first one. So when you get microseisms, those microseisms are caused by new cracks opening up in the ground, tiny ones. And those cracks allow new pathways for water and fluids in the earth to start moving. And one thing we've noticed is that right before some large earthquakes, water levels in wells rise as microseisms indicate that cracks are forming that allow water to more easily flow into wells and make their levels rise. So these are really two of the same things. The second one obviously has all the shortcomings of the first one. The video I showed at the end of last class on why earthquakes are so hard to predict talked about this third one, radon. Radon is a gas that naturally forms within the earth. And because it's a gas, and because the gas is in the earth, it's less dense than the surrounding rocks. And things that are less dense want to rise. So what happens when radon forms in the earth is it wants to rise up to the earth's surface. And it will do so through cracks and crevices in the rocks that this gas is forming in. And just like the first two, if you have a situation where the rocks start to crack a little right before the big earthquake, that allows new pathways for radon gas to move through the earth. This was first discovered about 20 years ago with bottled water in Japan. I don't know who thought of doing this, but somebody actually tested the radon gas levels in bottled water that came out of some rocks in Japan. And they found out that right before an earthquake, the bottled water had lots of radon in it. And it was probably due to these microseisms forming as small cracks form in the earth before the big earthquake, allowing radon to move more easily and get into the water systems. And this was talked about a little in the video that I showed on Tuesday. This next one is actually more of the same. It's all related to these microseisms, and this is electrical conductivity. This is kind of a fancy way of looking at how much cracking is occurring in the earth. And what scientists do is they basically pump some electricity into the ground. Rocks don't conduct electricity very well, but they do a little bit. So when you pump electricity into the ground, it actually flows a little bit through the rocks. And you can read on these fancy schmancy electrical conductivity meters just how much electricity is flowing through the earth. But right before an earthquake, you start to get microseisms as cracks form. The cracks actually prevent the flow of electricity and drop the electrical conductivity readings very suddenly right before an earthquake. But again, sometimes you get microseisms that happen too close in time to the large earthquake and therefore don't allow you to give a timely warning. And sometimes you get microseisms that occur and then just stop before the earthquake occurs. So again, none of these methods in any way, shape, or form are foolproof. One thing that's a little different is that we know that when you put stress on things, including rocks, that things tend to bend before they break. So I used that pencil example before, right? So if you take a pencil and flex it, it bends. But then at some level of bendiness, it snaps, right? And that's kind of where we're going with this idea here of ground strain. When you drill a hole into the earth that's circular or cylindrical, and then what happens over time as stress builds up in these areas is that the rocks tend to flex and make the round or cylindrical hole more oval in shape. And the hope is that, just like with the pencil, there's a certain degree of bending that it'll take before it breaks. We're hoping that there's a certain degree of ovalness, to think of it that way, within your drill hole that tells you when the rocks are going to break. This is still being actively studied. The problem with the Palmdale area is that it doesn't ever seem to have an earthquake that we can test it to. That area is just really locked for some reason and hasn't been willing to provide us with any examples that we can test some of our ideas on. I really like this last one. Animal behavior. So this has actually been noted for centuries. There's been reports of bizarre animal behavior hours to days before large earthquakes. It was reported that the night before the great San Francisco earthquake in the early 1900s that dogs were howling all night long, just making a horrible racket. This was widely reported to in a lot of places. I had a woman in one of my intro geology classes about 15 years ago who used to live in Southern California, and she swore on her life that her parakeet would warn her of earthquakes. It would start squawking and doing all sorts of crazy stuff, and she was absolutely sure of it. In fact, the Chinese have noted a few things. They noticed that snakes leave their holes, animals become skittish. There's strange behavior before some large earthquakes. And a few have even claimed that they can use it successfully to predict earthquakes. This has not been backed up by any statistical studies, sadly. And for me personally, hey, I have no doubts whatsoever that animals can sense things that humans can't. It's clear they can. You know, we have migrating birds that can sense either the Earth's magnetic field or whatever it is they use to navigate. And we don't sense that. I have no doubt that animals can sense things that we can't. What I have much less faith in, though, is that humans are smart enough to actually look at an animal and say, hey, that animal is doing something different because an earthquake is going to occur, or that animal is just being an animal today and doing weird stuff. My parents grew up on a farm, so I used to go visit my grandparents' farm all the time. They were dairy farmers, so there were lots of cows. I don't know if you ever watched cows for any length of time, but cows, they eat, they crap, they spaz around, and they eat, and they crap. And how do you know if a cow is spazzing around because an earthquake is coming or because it's just a cow? Like I said, they might sense things that we can't. I'm just not too confident that we're intelligent enough at this point to be able to look at their behavior and say, oh, that behavior means this at this particular time. Yeah? What's that?
If the whole herd is going crazy.
If the whole herd is going crazy, maybe. But that's the sort of thing you have to be able to look at these behaviors long enough and then have enough earthquakes follow so that you can have some sort of statistical confidence that what you're seeing is actually going to tip off that there's an impending earthquake. And earthquakes in a particular spot that you might be studying are actually still pretty rare events. I mean, worldwide there's obviously lots of earthquakes, but you never know where they're going to be at any particular day and point. So we really lack from data tied to individual earthquakes at this point. And that was the idea of going to Palmdale. It's like, okay, here's a spot. We know there's going to be an earthquake, but geez, we started going there in the 1970s because we knew there was going to be an earthquake. And now, 50 years later, it still hasn't happened. So sometimes the Earth doesn't cooperate with us on our time scale. Oh, this one. This one actually pains me to talk about. And it kind of goes back to what I was saying earlier about credibility. Because there's a story that goes with this that to a geologist is really sad and frustrating. So I'll explain this by sort of setting up the idea, the science behind the idea, and then I'll tell you how humans sort of screwed it all up. And we did. So this has to do with earth tides, okay? We know there are tides. All you have to do is live along a shoreline, and you know that twice a day the water levels rise and fall. And that tide is because of the gravitational attraction of the moon pulling on the Earth, okay? And the Earth pulling back on the moon. We also revolve around the sun. And our trip around the sun is not circular. It's eccentric, okay? It's elliptical. So at some times of the year, we're closer to the sun than at other times of the year. And remember, earlier in the semester, we talked about gravity, force of attraction between things that have mass. Well, the sun and the Earth have mass. But the gravity's stronger when we're closer together. So at certain points in our travel around the sun, we're pretty close to the sun. And at that time, the sun's gravity exerts more force upon us. So as we move around the sun, the Earth actually flexes a little bit. It sort of gets squeezed as we get close to the sun. And then you can think of it as relaxing a little as we get a little farther away from the sun. So it's kind of like squeezing an orange. So we're squeezing it a little bit. It's not a huge effect, but it's a small effect, and it's real. The bigger effect, as I mentioned just a minute or two ago, the Earth actually flexes as the moon revolves around it, and as we spin on our axis every day. This is the origin of our daily ocean tides. We know the oceans flex in response to it, but the Earth does too. It gets a little bit of squeeze. So you've got a little bit of squeeze from the Earth revolving around the sun, and then it's getting squeezed more frequently as the moon revolves around the Earth and as the Earth spins on its axis. So you get these little squeezes constantly, all the time. But every once in a while, we'll get a bigger squeeze than normal. If you live in ocean country, you know that some tides are bigger than others. Every once in a while, you get a couple of days where you get really big tides. And we seem to get this maximum flexure when the Earth is close to the sun, when the gravitational attraction is at its highest, and with a full moon. What a full moon means is that you have the sun here on one side, sort of the Earth in between them, and then the moon on the opposite side. So you got the sun pulling the Earth in one direction, moon pulling the Earth in the opposite direction, and then you get a super squeeze. You can think of it that way. You get this precise alignment where the sun and the moon are pulling on it in opposite directions. So we know the Earth gets squeezed. And in fact, if we look out on our solar system, there are some bodies out there that get squeezed so much that it completely affects how it behaves. And the best example of that is this moon of Jupiter called Io. Jupiter is our most massive planet, so it has a tremendous amount of gravity. Io is one of its moons, and it takes a nice elliptical orbit around Jupiter. Sometimes it's close and it gets a big squeeze, and then it gets farther away and it's a little relaxed and gets squeezed and relaxed. This little body gets squeezed so much and so frequently that it's the most volcanically active body in our entire solar system. Has hundreds of active volcanoes that go off every day, all the time. So we know this is a real process that can affect planets. There's some science here, okay? We know planets get squeezed by gravity as they interact with moons and interact with other planets and interact with the sun. So he's always getting squeezed. And every once in a while, they get kind of a bigger squeeze. So the idea is, will the Earth have more earthquakes when it gets a big squeeze? Okay? That doesn't mean that it's the cause of the earthquake, but maybe like along Palmdale, where it hasn't had an earthquake in some times, maybe we'll get a super squeeze, and that'll be just enough extra stress to make this big earthquake happen. Even to scientists, this is a very plausible idea, and it's something that's been studied. So we look statistically, are there more earthquakes and volcanic eruptions when we have full moons? And the statistics are inconclusive. Some people swear there's a little trend there, and other scientists are like, yeah, it's just too weak. It's not a huge effect, at any rate. Maybe there's a little something there. At least we have an explanation for it, right? Okay, so nothing wrong with what I've talked about so far. The problem with this is that somebody about 25 years ago, kind of a rogue scientist, went on TV about 2 weeks before a full moon and boldly predicted that the New Madrid, Missouri fault was going to be triggered by an earth tide. We mentioned New Madrid just a little bit a couple of class periods ago when we were looking at the map of where earthquakes form in North America. And this is this cluster of earthquakes down in southern part of Missouri, not far from St. Louis. It gets occasional earthquakes. It gets occasional earthquake swarms. But the last time it had a big, massive earthquake was a little over 200 years ago. Back in 1811, and it was big. We didn't have modern-day seismometers, so we're only guessing at the magnitude, but it was right there with the biggest ever on record. Magnitude 8.5 to 9. An earthquake that big, total devastation if your buildings aren't built to withstand earthquakes, and maybe total devastation even if they are. So back in 1811, this was a sparsely settled area. In fact, this was right on the edge of the American frontier. Just a few years earlier, Lewis and Clark had set off from St. Louis to explore the Louisiana Purchase, the western U.S., actually where we are here. So this was not a heavily populated area at the time. It was right on the edge of white civilization from the early 1800s. but it was a huge earthquake. The Mississippi River flowed backwards for a while. Boats were thrown out of the Mississippi River onto shore. The Mississippi River changed its course completely, and one of the big bends in the Mississippi got cut off from the river itself and became the lake called Reelfoot Lake. So it had a huge effect on the landscape. And it was felt all over the eastern U.S. It was so big that church bells rang in Philadelphia, 1,000 miles away. Again, probably the biggest in the lower 48 in the last couple hundred years. Not something to be taken lightly. The area today is much different. Now this is right in the middle of the country. We have a major city, St. Louis, big suburban area tied to it. There's about 12 million people that live in the area between New Madrid, Missouri and St. Louis, Missouri. A lot of folks that live there. And if you're from this area, you know about this. You know about this earthquake. It's not something people were ignorant to. People who live there knew about it. And in fact, back in 1987, there was a swarm of small earthquakes, a swarm of microseisms. And people knew about that. You know, it's like, ooh, this could be this could be the precursor to a big earthquake. So it put people a little on edge, okay? So this is 1987. But like with many earthquake swarms, there wasn't a big earthquake that followed. So people got on edge and then nothing happened and things sort of died down until this guy, Iben Browning, Dr. Iben Browning, which is funny because he's a climatologist, not a geologist. It's a little bit like Alfred Wegener. He was dismissed because, in part, he wasn't a geologist when he was talking about continental drift. Well, Iben Browning is not a seismologist. He's a climatologist. And I don't know if anybody figured out why he did this, but he decided to call up one of the local St. Louis news stations and said, I'm scientist Dr. Iben Browning, and I am predicting that there's going to be a massive earthquake on December 3rd, which is a few weeks away, that's going to be caused by earth tides. This is going to be one of the biggest tides we've had in decades, and it's going to be enough to trigger this fault. Well, people in general, if you look at levels of trust in the American population, scientists are among the most trusted of professions. At the very bottom are bankers and lawyers, and at the very top are scientists and doctors. People trust scientists. And I think most scientists are trustworthy. But we're people. Sometimes we make mistakes, and some scientists just aren't very good at what they do. And sometimes scientists are maybe in this whole thing for the wrong reason. I don't know what was going on with Iben Browning at the time. I don't know why he did this. But he made this bold prediction. And of course, the people in the area know about this fault. And they were a little on edge. This was, I think, in 1989. They were a little on edge from the earthquake swarm a couple years earlier. They canceled school for a few days. Some people even sold their homes because they had just had enough. They had had enough of the earthquake talk. They had enough of the small earthquakes in the area. Some people just decided to hang up shop. And guess what happened? Not a damn thing. Nothing. Iben Browning was somewhere in the Caribbean on December 3rd, nowhere to be found. It was a disaster, and You can say, well, nothing happened, no harm, no foul. But yeah, it's foul if you're a scientist and you're trying to come up with strategies for predicting these things and warning the public, and then you have somebody that goes and shoots your credibility, because general public just sees scientists as a group. They don't see, oh, you have a scientist here who's a little out of his element. They just say, oh, scientists can't be trusted. I'm not going to listen to them next time. So when it comes to prediction, and we'll see this when we talk about volcanoes next week, it's really important to get it right. Some people say, well, a volcano starts erupting, we should just evacuate everybody at the first sign. We're going to talk about why that does not work, why it's actually counterproductive. When you make a volcanic prediction, it better happen, or you blow your credibility, and then the next time, more people actually die. Yeah, you have a question? No? Okay. All right. Okay, so at this point, we know earthquakes are going to happen. It'd be nice if we can predict them, so we can give warning. Bottom line is we can't. And then once they happen, they just move too fast to give anybody any adequate warning. So, what's left for us to do? Well, if we can't predict these things, this is sort of the human tendency right here. We love to mess with nature. And if we can't predict it, well, maybe we can control it. Maybe we can get the upper hand on Mother Earth. Maybe we can unlock these faults. Talking about that seismic gap near Palmdale, we know stress is built up. We're pretty confident that the next time an earthquake occurs, it's going to be monstrous. It's been building up stress for over 100 years. It sure would be nice if we could go in there and relieve some of that stress so that the next earthquake isn't completely devastating. Can we control earthquakes? Well, as a matter of fact, to a small degree, and maybe even a large degree, we can. And we've actually done it by mistake several times. This first one I put up is completely ridiculous, but nevertheless, it's something that's been proposed because, we built all these wonderful nuclear weapons back in the 1950s and the aftermath of World War II, and you just have some folks in our government that just really want to use these things, And geez, if we can't start a war and use these things, then maybe we can use it for something else. And some people have actually suggested that we tunnel down into some of these fault systems, put a few nukes in there and detonate them. The idea is that the massive explosion will break enough rock to weaken the fault and allow it to slip. And then, sure, it'd be a big earthquake, but you could give people warning, It's like, we're going to go and blow this thing up next Tuesday. Don't go to work. Go visit your grandparents out in Wisconsin or something. Luckily, this isn't seriously considered anymore. Detonating a nuclear weapon in the ground where water flows and people eventually drink that water is just a stupid idea. So it's not seriously considered anymore. But every once in a while, somebody comes up with this idea. You hear this with volcanoes too. Why don't we just drop bombs on volcanoes and try to get them to erupt when we want them to erupt? And it just doesn't work that way. These nuclear blasts pale in comparison to some of the processes that occur down in the earth. Sure, they're powerful and all, but they're typically not powerful enough to trigger a volcanic eruption. And I don't know if they'd be strong enough to even trigger an earthquake in this situation. So this diagram that I have here on the left is of the San Andreas Fault. So this red area down here around LA, this is a section of the fault that's been mobile. They've had lots of earthquakes over the last 100 years. This area of the fault up near San Francisco that's depicted in red, that's had lots of earthquakes over the last 100 years. several magnitude 7s. But then there's this little section right here. We've got Parkfield, Palmdale's out there as well. They haven't had an earthquake there. There's been earthquakes all up and down this lower section, all up and down this upper section. So you know parts of it are moving, and then this part is just sticking. So this is the part where we think can launch a big earthquake. And there on the right is what that area looks like from the air. You can actually see the fault zone because of the lack of vegetation. But like I said, we have actually triggered lots of earthquakes by accident. And there's a potential we could use this as an earthquake control mechanism. And the idea is that you pump water into these fault zones under really high pressure, and that actually lubricates the fault and allows it to slip a little easier. The first place I know of this actually happening is right here, just outside of Denver, back in the 1960s. This happened at the Rocky Mountain Arsenal, which is out near the airport. All of a sudden, we're getting lots of earthquakes at the Rocky Mountain Arsenal, hundreds a day. They weren't huge. Most of them are in the magnitude 2 to 3 range, but there were actually a couple of magnitude 5 earthquakes. That'll get your attention. That'll knock stuff off the shelves, crack your walls. So you're a scientist, and suddenly all these earthquakes start happening in one little place west of Denver that happens to be a military installation. That seems suspicious. And it was suspicious. And the media looked into it and started asking questions. And actually what was happening is the military was pumping liquid waste into the ground to dispose of it. And they just happened to pump it into a fault zone that they didn't know about. It lubricated the fault zone and started shifting, and then the ground was just shaking pretty much all the time. Because remember with earthquakes, as you go up the Richter magnitude scale, you increase the shaking by an order of 10. So the difference between a magnitude 3 and 4 is 10. The difference between 3 and 5 is 100. Difference between 3 and 6 is 1,000. Difference between 3 and 7 is 10,000. Can you imagine the number of earthquakes it would take to relieve a magnitude 8 earthquake? The ground would essentially have to shake all the time. And what residents found is that really sucks. It sucks to have the ground shaking all the damn time. And you can't control it to the point where it's like, oh, let's just have ourselves a whole bunch of magnitude 2s. No, you get some magnitude 2s, but then you get a magnitude 5 and it damages your house. And I think people who lived at that time in that area pretty much came to the conclusion that this is just not how I want to live my life. I just wouldn't want to live where the ground is constantly shaking. Stuff is constantly falling off of my shelves. Things are constantly getting damaged. The sidewalks are getting broken. The roads are getting broken. It's like maybe it's just better to deal with a large earthquake every once in a while. So we suck at predicting earthquakes. Controlling them causes maybe as much trouble as just letting one big one go through every once in a while. So that's kind of where we are today. We could control them to some degree if we wanted to, but let's face it, we probably don't want to. And we can't predict them. So we are stuck with living with them, and they surprise us once in a while. And sadly, they cause a lot of death and destruction once in a while. I'll finish this chapter just showing you, here's a map of where we have earthquakes in Colorado. The biggest one, again, back in the late 1800s, just outside of Fort Collins, up near magnitude 7. You can see the swarm here. This was the Rocky Flats swarm that I just talked about. You can see swarms in other places, and now we're getting swarms from fracking installations being set up. Because what fracking does is it pumps high pressure water into the ground, and sometimes that high pressure water interacts with fault zones and makes them slip. We've had several magnitude 4 earthquakes right around here in Greeley over the last several years. Every one of them have been associated with a fracking operation. So we could potentially control earthquakes, but just having the ground shake all the time is just not fun, so we probably won't. Do you guys have any questions? Okay, just give me a minute to boot up the next chapter and then we'll get restarted.